So welcome to the continuity session of Introduction to Reinforced Concrete Element. In today's session, we are going to see about the flexure, shear, torsion and bond behavior of reinforced concrete elements. And also we are going to see about the serviceability requirements which is needed for the reinforced concrete. So the behavior of RC beams in flexure. If you are going to consider a beam like this, when you apply an UDL load on the top, then the beam will bend like this. That is, flexure is nothing but bending of the beam. So in this, the tension will develop at the bottom portion and the compression will created at the top portion. So in order to overcome the tensile stress or tensile cracks at the bottom, we will provide the reinforcement. So this steel reinforcement will carry the tensile force at the bottom and the concrete will withstand the compressive load at the top. So neutral axis concept, because as I have already told that neutral axis is the point where the stresses will be zero, because if you are considering this particular beam like this rectangular beam, then the neutral axis, above the neutral axis it will be subjected to compression and below neutral axis it will be subjected to tension. But at the neutral axis point, at this point the stresses will be zero. So neutral axis separates the compression and tension zone and the stresses or strain is zero at the neutral axis. And this position of neutral axis is determined by the amount of reinforcement provided in the reinforced concrete element. So type of sections, we have three different types of sections. One is under reinforced section, balanced section and over reinforced section. In under reinforced section, the steel will yield first, and in over reinforced section the concrete will crush or fail first. And balanced section, the concrete and the steel will attain their breaking point same time. So here if you consider the steel failure, as I already told, the steel will undergo elongation and it will form a necking before failure. So it will give the warning that the structure is going to collapse. But if you consider the balanced or over reinforced section, where the concrete will fail, as I have already told, the concrete will fail in brittle nature. So the failure will be sudden and we can't have a particular time to evacuate that building. So here if you see the under reinforced section, it will have ductile failure, and the balanced section will have ideal or brittle failure, and over reinforced section will have brittle failure. So here if you see,
let's explore reinforced concrete beams. Under reinforced sections provide ductile failure. Over reinforced sections fail catastrophically, always designed for ductile failure.
so this video explains why we need to design for a under reinforced section, because generally we need to design only under reinforced, because the under reinforced section will only provide the warning and it will provide a sufficient time for evacuation of the building if it is undergoing failure. So shear behavior means the diagonal cracks which will develop at the nearer to the support, not at the support, it will be created nearer to the supports. Here if you see, the crack is formed at 45 degrees. So this 45-degree cracks will represent the shear failure of the structure. In order to overcome this shear failure, we need to provide the stirrups which will support the concrete to hold it in position and overcome the additional shear. Shear reinforcement, there are three types of shear reinforcement. We will have vertical stirrups, inclined stirrups, bent up bars. And here if you see in the first picture, the vertical stirrups means the stirrups are provided. Stirrups are nothing but the rings which they have provided here. So the stirrups are provided in vertical direction. Here if you see, the stirrups are provided in the inclined direction at 45 degree. And here the bent up bar means we will have the stirrups vertical bar and also we will have an inclined bar. So in practical scenario, we will go with the vertical stirrups which will be easy to manufacture and which will be easy to tie at the site. And torsion in beam. So when a structure is loaded When a structure is loaded eccentrically, then it will have a tendency to rotate. So the twisting of the member creates the torsion moment, as I mentioned here. So it is common in edge beams and curved structures. The edge beam, the beam which is provided at the edge of the building, or the curved beams will have a tendency to create or undergo torsion. So in order to overcome torsion, we need to provide additional longitudinal bars and stirrups to overcome the torsion. So here if you see, torsion, when torsion acts on a structure, torsion won't alone act on the structure, it will act along with the shear and bending, that is flexure. So it's a combination. When the torsion is acting on a structure, it is a combination of torsion, shear and flexure which will act together in the structure. So next one is bond between the steel and concrete. As I already told, to transfer the load from the concrete to steel or steel to concrete, it will happen only through the bonding between these two elements. Here if you see, we have provided the steel and the steel is connected to the concrete. So by this particular bonding only, the load is transferred from the concrete, because generally directly the load will act only on the concrete, and from concrete only the load get transferred to the steel. So here how the load is transferred from concrete to steel means by this bonding. So next one, development length. So development length is the length required for the reinforcement to develop its full strength. That is, in order to transfer the load from the one element to the another element, we will provide this development length. Here if you see, in this we have a beam and we have a column. Here the beam reinforcement is extended into the column. Here if you see, in this L shape, and here at the bottom if you see, we have another one L shape. So by providing this L reinforcement, that is, it is called as development length, and by this reinforcement helps to transfer the load from beam to the column, and also it will helps to create the or develop the full strength of reinforcement in order to carry the load. So this development length is also called as anchorage length, which will help to carry the load. So here if you see, the anchorage provides proper force transfer at the bar ends. Next one is lap splicing. In lap splicing, the lap splicing is nothing but combining of two rods. Why we need to combine two rods? Because a single rod is of 12 meter length. If a building is going to be more than 12 meter, or if a single element is going to be more than 12 meter, then we need to join the two rods together. So in order to join two rods, we have three different methods. One is lap splicing, another one is mechanical splicing, and another one is welding splicing. So lap splicing means, what we will do is, we will take one bar like this and we will bend it in this shape, and we will take the another bar and we will bend it in this shape, because here if you see, we have a small groove and it is bended like this. In this bend, this region is nothing but this particular region, 40 to 50 times the diameter, larger diameter of the bar combined together. So here if you see, the center of gravity of the bar at the top and center of gravity of the bar at the bottom will be in the same line. So we need to bend the bar in such a way that the center of gravity of both the bars should be aligned in the same vertical line. So this is the normal lap splice. Next one is mechanical splicing. In mechanical splicing, we will use a coupler to join the two rods. At the end of the rod, we will provide the threading and we will join the two rods together. So this is nothing but the mechanical splicing. And third one is welding splicing. Welding splicing means, what we will do is, we will place the two rods and we will apply the weld and we will join the rod together. So this is called as welding splicing. In Indian scenario, we will mostly use the lap splicing. So next one is curtailment of reinforcement or cranking of reinforcement. So in order to overcome the tensile load, we will provide the reinforcement. So if you consider a beam, the tensile reinforces will be maximum at the bottom, and why the tensile load is maximum at the bottom means, due to the flexure, that is due to the bending of the beam, the tensile load will be maximum at the bottom. And here the bending will, if you are considering a beam like this, then if it is undergoing bending like this, then this particular zone only will have the higher tensile load, and these remaining zones will have the lower tensile load. So in order to make economical use of the reinforcement, we will go for either curtailment or cranking. So curtailment means we will cut the bar and we will use it for somewhere else, and cranking means we will bend the bar and we will use it somewhere else. So here if you see, we are having 3 number of 12 mm dia bar, and here if you see 2 bars are provided straight line and 1 bar, the black line represent the curtailment, because the rod is cut it at the point where the maximum tension is there, we will provide the bar, and where there is low tensile force we will cut the bar and we will provide it somewhere else. Here if you are considering a fixed beam, then the fixed beam will bend like this, right? So if it is undergoing bending like this, then here we will have the maximum tensile force. So we have provided the reinforcement at the bottom, and at the ends we will have the maximum tensile force at the top. So we have provided the reinforcement at the top. So here if you see, we have the single reinforcement, and by cutting it at the required places, we are using for both the zones, tensile zone at the bottom and the hogging moment which is created due to the fixed support at the end, we are using there also. So this process is called as curtailment, because the rod is cut here. Cranking means the rod is bent at 45 degree. Here the angle is 45 degree. Here the angle is 45 degree and the rod is cranked here. So here if you see, instead of cutting, what we do is we will bend the bar at 45 degree and provide the reinforcement at the top. So where we will use curtail means when the dia of the bar is larger, we will go for curtailing, that is cutting, and when the dia of the bar is smaller, we will go for the cranking, because cranking needs a more manpower, and when the bar size is small, cranking is easy. When the bar size exceeds a certain limit, then the cranking is difficult, where we will go for the curtailment. So next one is serviceability requirements. What are all the expectation of a reinforced concrete elements or structure? It need to have a controlled deflection, it need to have a controlled cracking, and it need to have good durability, because it need to have a good lifetime, and it should have a proper cover requirements, and also it needs to withstand the vibrations. These are all the serviceability requirements of a normal RC building. Next, deflection control. So with this we come to the conclusion of the session introduction. With this we come to the end of the introduction to reinforced concrete elements. Next we are going to see about the beam, and we will see the concept of the beam, that is what are the different types of beam, then we will solve the problem. Thank you.